With a binomial probability distribution, you can also calculate mean and standard deviation, and that's what we're going to look at in this video. The equations are here at the top. So the mean for the binomial distribution, you can see that we are using population symbols. So mu is the mean, equals n times p, the number of trials times the probability of a success. The variance, or sigma squared, is n times p times q, and then you take the square root of that to find the standard deviation. There's a little bit here about unusual values. Again, in the previous video, I said to look for a cutoff value given in the problem. And it could be 0.05, it could be 0.01. There's lots of different cutoff values that are possible, and any probability that's smaller than that would be unusual. So our first example is looking at a statistic about graduation rates from high school in the United States. Alright, so the first one here is find the mean and standard deviation for the number of high school graduates for a sample of 1,000 people in the United States. So we have 88% that graduate from high school, and that's a probability of success if we define success as graduating from high school. And let's convert that to a decimal so that we can work with it in our equations. 0.88. A sample size, that's like a number of trials, that's going to be n. And the equation for mean for binomial distribution is mu equals n times p. So all we need to do is take n, 1,000, times p, which is 0.88, and we get 880 people. So that would be the mean number of people, or expected number of people out of 1,000 that have graduated from high school. So the second question, if you took a sample of 1,000 people and found that 820 of them graduated from high school, would the value of 820 be unusual? And again, every sample is going to be different, and we can say if something is unusual or not by comparing it to our expected value. So again, we have a sample of 1,000 people, it's going to be n. 820 graduated from high school, so 820 is x. And we want to know if that's unusual, and our percentage is the same, so p is still 0.88. And here, when it's asking about something being unusual, we need a probability. So we're going to go back to our binomial probability formula. And you could use the one with the factorials. In that case, you would need q. So let's just do a quick reminder that q is 1 minus p, or 1 minus 0.88, which give you 0.12. And you could plug all those numbers into the binomial distribution formula. Or we can just use our calculator. So the probability of x being 820 is, using our binomial PDF function, n is 1,000, p is 0.88, and x is 820. Look at this distribution function using 1,000, 0.88, and 820. And you'll see you get a really tiny probability. This is not necessarily what you would expect. But if you think of, so I'm just going to use less than 0.001 because that was such a small number. But if you think of a sample of 1,000, you could get any number from 1 to 1,000 as your result for x. So the probability of any single x is going to be very small. So you could say that's unusual because again it's less than 0.0001. That's unusual. But would you suspect the reported percentage of 88% is incorrect? Out of 1,000, 820 out of 1,000 or 880 out of 1,000 to get 88% doesn't really seem like that much of a difference. So I wouldn't suspect that that number is incorrect. And I just want to show you with the calculator, if you, instead of out of 1,000 people getting 820, if we use the same ratio, like 82 out of 100, our number ends up being a little different. And then you'll kind of see what I'm getting at, where that one number x, that 820 out of 1,000, is fairly unusual in that respect. But the ratio, 820 out of 1,000, is not really that different from 880 out of 1,000. So let's just try a different version with the same ratio. So 100 instead, the percentage would still be the same. And then if 82 out of the 100, now we have 0.0228 for our probability. That's not all that unusual. And it's the same ratio. It's just that when you're picking out of 1,000, you could get 820, 821, 822. There's so many more possible outcomes that the value for any one particular x ends up being very small. So I wanted to show you that one just so that you could see if that ever happens to you and you get a number that's much smaller than you expect, why that might be happening. Okay. So let's move on to the second one. So example 2 has to do with taking a multiple choice quiz. It has 6 questions. Each of them has 4 options. And if you have no idea what the answers are, you're just guessing. So the probability of getting 3 correct answers, okay, and remember there's 6 questions, so 3 out of 6. So there's 6 questions, it's n. Getting 3 correct or 3 successes, that's going to be x. And our probability, p, since each has 4 options, the probability of selecting the correct one is 1 out of 4 by guessing, which gives you 0.25 or 25% chance of guessing correctly. Alright, if you were using the binomial distribution formula with the factorial symbols, we would need q, which would be 1 minus p, would give you 0.75 or 75% chance of getting the answer wrong. Okay. So we're just going to use the binomial formula, or the function in the calculator. N is 6, p is 0.25, x is 3, and this would be the probability of 3 correct. So n is 6, probability of success is 0.25. And x is 3. So the probability that you would guess 3 of them to be correct is 0.1318. About a little over 13% chance of getting 3 correct out of 6. Okay. So the next question is an at least question, at least 3 correct. So that would be if you got 3, 4, 5, or all 6 out of 6 correct. And my recommendation for a problem like this is just to calculate each of them. So we just did 3. So we only have to do 3 more, and then we'll have all of them and we can add them together. And 6. And if you did this in the calculator, I'm just going to write down the answers just to save some time. And you can try these in your calculator just to check that you get the same thing. You get 0.033, 0.004, and 0.0002. And if we add all 4 of these together, the probability of 3, 4, 5, and 6, we get 0.169. You could also, remember the other 3 options are 0, 1, and 2. If you, this would be the complement. So you could just do the probabilities of 0, 1, and 2, add them up, and then subtract from 1. So sometimes for the at least questions, either way you do it is the same amount of work. Sometimes the complement is less work, and just check that before you start. The next one, the expected value for the number of correct answers, the mean. Remember, mean is expected value. And we know that that's n times p. N is 6, there are 6 questions. P is the probability of guessing one correctly, 0.25. So the expected number that you would get right by guessing is 1.5 out of the 6. And the standard deviation, square root of n times p times q. So n was 6, p is 0.25, q is 0.75. So 6 times 0.25 times 0.75, enter, and then do second squared for the square root sign, and put our answer back in, second answer down here, hit enter, and we get 1.06 is our standard deviation. And if we put labels on, we'd expect to get 1.5 correct answers with a standard deviation of 1.06 correct answers.